Our home, planet Earth. It feels solid beneath our feet, doesn't it? A steadfast, unmoving stage for the drama of life. But this perception, like so many, is an illusion born of our fleeting human timescale. The Earth is, in fact, a dynamic, restless body. Its surface is constantly shifting, buckling, and renewing itself. Mountains rise and fall, oceans open and close, continents waltz across the globe in a slow, majestic ballet that spans eons. This is the grand narrative of plate tectonics, a story written in stone and fire, a story that continues to unfold. The Earth's outermost layer, the part we interact with directly, is called the crust. It's thin, remarkably so, like the skin of an apple. Beneath the continents, this crust can be tens of kilometers thick. Under the oceans, it's much thinner, perhaps only a few kilometers. This crust, along with the uppermost rigid part of the layer below it, the mantle, forms what geologists call the lithosphere. Think of it as a collection of giant rocky rafts floating on a sea of hotter, softer rock. These rafts are the tectonic plates. Understanding this is key to understanding Earth. So what are these tectonic plates? Imagine the Earth's lithosphere. That rigid outer shell isn't a single unbroken sphere. Instead, it's fractured into about a dozen major plates and many more minor ones. These pieces fit together like a giant spherical jigsaw puzzle. Some plates are enormous, carrying entire continents and vast stretches of ocean floor. The Pacific plate, for example, is the largest, underlying most of the Pacific Ocean. Others are smaller, but no less significant in the grand geological scheme of things. These plates are not just the crust. They are composed of the crust, the uppermost, rigid part of the mantle. This combined layer, the lithosphere, can be up to 100 kilometers thick, sometimes more under old continental regions. There are two main types of lithospheric crust. Continental crust is thicker, less dense, and primarily made of granitic rocks. It forms the land masses we live on. Oceanic crust, found beneath the oceans, is thinner, denser, and composed mainly of basaltic rocks. This density difference is crucial for how plates interact. Let's explore how these plates move. One fundamental way is when they move away from each other. We call these divergent boundaries. Imagine two massive conveyor belts moving in opposite directions, carrying the plates along with them. As the plates pull apart, a gap is created. This isn't an empty void though. Hot molten rock or magma from the mantle below rises to fill this space. As this magma cools and solidifies, it forms new crust. This is how new oceanic lithosphere is born. The most prominent examples of divergent boundaries are mid-ocean ridges. These are vast underwater mountain ranges that snake through all the world's oceans, like seams on a baseball. The mid-Atlantic ridge, for instance, runs down the center of the Atlantic Ocean. Here, the North American and Eurasian plates are moving apart, and the South American and African plates are doing the same. This process, known as seafloor spreading, continuously adds new material to the ocean floor, gradually widening the ocean basins over millions of years. Now, if plates are moving apart in some places, they must be coming together in others. These are called convergent boundaries. Here, two tectonic plates are on a collision course. The outcome of this collision depends heavily on the types of crust involved, specifically whether they are oceanic or continental. The forces at play are immense, capable of building the tallest mountain ranges on Earth and triggering some of the most powerful earthquakes ever recorded. Consider what happens when two plates carrying continental crust collide. Continental crust is relatively light and buoyant. Neither plate wants to sink or subduct beneath the other. So, like two massive bulldozers crashing head-on, the crust buckles, folds, and thickens. The result is the formation of immense mountain ranges. The Himalayas, the world's highest mountain system, are a spectacular example. They were formed, and are still being formed, by the collision of the Indian plate with the Eurasian plate. This process began tens of millions of years ago and continues today. Section 5. The subduction zone, where worlds collide and one descends. Subduction is a fundamental process at many convergent boundaries. It occurs when two plates collide and one, the denser of the two, is forced beneath the other into the mantle. Think of it as one massive slab of rock diving deep into the Earth's interior. This usually involves an oceanic plate, which is denser than continental crust. The region where this happens is called a subduction zone. These zones are geological hotspots characterized by deep ocean trenches, lines of explosive volcanoes, and powerful earthquakes. When an oceanic plate collides with a continental plate, the denser oceanic plate always subducts. As it descends, it begins to heat up and release water trapped in its minerals. This water lowers the melting point of the overlying mantle wedge, causing it to melt and form magma. This buoyant magma then rises through the continental crust, eventually erupting at the surface to form a chain of volcanoes, often called a volcanic arc, on the continent. Section 6. Sliding by, the friction of transform boundaries. We've seen plates move apart and plates collide. There's a third way they interact. They can slide horizontally past each other. These are known as transform boundaries, or sometimes strike-slip boundaries. At these locations, lithospheric plates move roughly parallel to the boundary but in opposite directions. Unlike divergent boundaries, no new crust is created. Unlike convergent boundaries, crust is not consumed or destroyed. Instead, the plates just grind past each other, a process fraught with friction and tension. The movement along transform boundaries is not smooth. The massive rock plates don't just glide effortlessly. Instead, their rough edges tend to lock together due to immense friction. As the rest of the plates continue to move, strain builds up in the rocks along the locked section of the fault. This stored elastic energy accumulates over years, decades, or even centuries. Eventually, the strain overcomes the friction and the rocks rupture, snapping forward suddenly. Section 7. Continental drift, a slow dance through millennia. The idea that continents move is not entirely new. As early as the 16th century, mapmakers noticed the jigsaw-like fit of the coastlines of Africa and South America. In the early 20th century, a German meteorologist named Alfred Wegener championed the theory of continental drift. He proposed that the continents were once joined together in a single supercontinent he called Pangaea, meaning all Earth. He gathered evidence from matching fossils on different continents to similar rock formations and ancient climate data. Wegener's ideas were initially met with skepticism, even ridicule by much of the scientific community. The main sticking point was the lack of a plausible mechanism. How could massive continents plow through the rigid oceanic crust? It seemed impossible. It wasn't until the mid-20th century, with the discovery of seafloor spreading and the development of plate tectonic theory, that Wegener's core idea of moving continents found its mechanical explanation. The continents weren't plowing through anything. They were passengers on the moving lithospheric plates. So the continents are indeed drifting, but as part of these larger plates. Section 8. Beneath the surface unveiling superhot mantle plumes. While plate boundaries are the primary sites of geological drama, there's another fascinating phenomenon occurring deep within the Earth mantle plumes. These are columns of exceptionally hot rock that are thought to rise from the deep mantle, perhaps even from the core mantle boundary, some 2,900 kilometers beneath our feet. These plumes are relatively stationary compared to the moving tectonic plates above them. When a plate drifts over one of these hotspots, it can lead to significant volcanic activity in the middle of a plate, far from any boundary. The Hawaiian Islands are a classic example of hotspot volcanism. The Pacific plate has been slowly moving northwestward over a stationary mantle plume for tens of millions of years. As the plate moves, the plume punches through it, creating a chain of volcanic islands. The oldest islands, like Kauai, are to the northwest and are no longer active, having moved off the hotspot. Section 9. Shaping our world. The enduring legacy of plate tectonics. Plate tectonics is more than just a theory, it's the grand unifying concept of modern Earth science. It provides a comprehensive framework for understanding the myriad geological processes that shape our planet, from the majestic rise of mountains to the terrifying tremor of an earthquake. It explains why volcanoes erupt where they do, why oceans open and close, and why continents are not fixed in place but are on a perpetual journey across the globe. It connects seemingly disparate phenomena into a coherent dynamic picture of Earth. The legacy of plate tectonics is written across every landscape on our planet. The distribution of continents and oceans, the topography of the seafloor, the location of mineral deposits, and even the long-term patterns of climate are all profoundly influenced by the movement and interaction of these massive lithospheric plates. The very air we breathe and the water we drink are tied to geological cycles that are, in part, driven by tectonic processes. The evolution of life itself has been shaped by the changing configurations of land and sea as continents merged and separated, creating new environments and new challenges. Understanding plate tectonics is vital for mitigating natural hazards.